This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
How does the switch work? Great, thanks. So as Marco mentioned, he's also around, right? So for all the questions that we weren't able to cover right now, please just feel free to approach him throughout the week. Now, Matthew, you can already stay here, right? And take the mic, set it up. I will quickly change the presentations. So here you go. So Matthew is a final year PhD student, as we heard, so we already heard that you should hire him already, right? He's a Rhodes Scholar at the University of Oxford and a recent graduate research assistant at the Los Alamos National Laboratory. At Oxford, his research has focused on near-term quantum algorithms, and at Lano, he has worked on quantum sensing and classical simulability in quantum computing, and excited to hear you talk now.
Cool. Can everyone hear me? Great. Okay. So, g'day everyone. Lovely to see everyone, all these lovely big brains gathered in my home country. As Krista said, I'm a PhD student at Oxford in Simon Benjamin's group. During my PhD, I've spent a lot of time working with Marco. This work actually began through the summer school, which I loved. It was probably the best thing I did in my PhD. So please, if you're thinking of applying, you should apply. Now, of course, Marco is always a very hard act to follow. But I am very fortunate that his talk sets up a lot of the context for mine. So today I'll be talking about Lie-algebraic classical simulations in variational quantum computing and QML in this framework that we call GSIM. So this work was done with the dream team from Lano, Martin, Lukasz, Marco, and Fred, all of whom are here, so please come talk to us. So Marco has told you a lot of the story so far. And it seems that there's this deep connection between trainability and simulability in QML. But in the individual cases where barren plateaus are provably absent, not only do we have some degree of classical simulability, but the mathematical tools that are used to prove the absence of barren plateaus are also typically used for the classical simulation itself. And so this is a sort of like case-by-case observation that's held up by a number of different pillars. And so today my talk will be about one of these specific pillars. So we'll assume pretty much the same setting that Marco was talking about, standard setting with a variational ansatz circuit consisting of parameterized rotation gates in this sort of like repeated layered structure. We'll take some input state, rho, we'll evolve it by some circuit, u, and then we'll compute an observable O. And of course, in a general QML setting, you might have many different data states, rho, many different observables, O, but all of the terms that you care about on a quantum computer are going to look like this. And so this term should be thought of as a Hilbert-Schmidt inner product. And in the Schrödinger picture, this is a product between this evolved state and a measurement operator. But more usefully for our cases in the Heisenberg picture, you can think of this as evolution between some input state and a backwards evolved Heisenberg operator. So let's think about the latter and follow on from this question that Marco asked, which is that as this thing evolves, as this operator evolves, where can the operator go? And so we've got this like inner product between these two terms. And as we're optimizing, what we're trying to do is we're trying to anti-align these two things in this potentially exponentially large space. And this inner product meets in the middle here. And in general, because we can have exponentially many terms, this could be exponentially small, and then we get a barren plateau. So again, if we take this input state rho and we expand it into a general basis, in general this just could be exponentially large. But if this observable is evolved by unitary, maybe it's the case that this unitary can't take it just like anywhere in the Hermitian operator space. So maybe we have some symmetries or lack of expressibility that will constrain it to only move around in some smaller subspace. And if that subspace is only polynomial in the system size, then the ansatz is going to lack the expressive capability that can cause a barren plateau. But then, as Marco said, if we think about this smaller subspace, and if we, instead of doing the sort of full Hilbert space picture, we track individual objects that are moving around on this small subspace, then that is often the foundation for some sort of classical simulation technique. And so this subspace, in our case, is going to be built around the dynamical Lie algebra, which we denote here as G. It's a vector space that is built from the gate generators for the rotations, and then all the terms that are generated by their nested commutators. So here we can think about the simplest possible way that we could compute our dynamics with this. So if we take some input state, rho in, and we evolve it under this unitary channel, and then we think about the dynamics of an observable. Now we're going to assume that this observable is expandable into the Lie algebra, that is, it's supported by the Lie algebra. Then we're going to do our Heisenberg evolution. And so if our unitary is generated by Lie algebra elements, that is to say, if the unitary is part of the Lie group under consideration, then this will just generate more terms of the Lie algebra. That is, we have closure under this operation. And so because we have closure, this can then be expressed as a linear combination of these basis elements of the Lie algebra. Our evolved observable will admit this form. And these UJK coefficients, they're quite easy to find in the adjoint representation of the algebra. In fact, these coefficients are just the structure constants of the algebra. And so let's call this evolution method GSIM, named for the dynamical Lie algebra G. And if the dimension of this algebra is polynomial, then these sums are only going to be polynomial in n in size, and this approach is going to be classically efficient. You can do this for any algebra, but in general, they might be exponential in size. And so with that, I've plotted the memory requirements for a particular instance of GSIM versus some expensive exponentially scaling state vector methods and density matrix methods, and then just compared this to a couple of other efficient classical methods. And so when we have a polynomial algebra, this will be efficient. And it's also worth asking, like, what kind of systems are going to admit a polynomial algebra? And indeed, you don't need many operations to get universal quantum computing, so this is a fairly small set. The ones that we really care about are free fermion mappable transformations, and permutation invariant systems will both give you polynomial algebras. So despite these constraints, these applications that follow are going to be largely about what can we do with a smaller set of operations where we have this classical simulability. But we can in fact push this formalism a little bit further than just the observables that are supported by the Lie algebra. So if we have any symmetries at all in the unitary rotations that we're applying, then the operator space will decompose into a direct sum of these invariant subspaces. If you went to Martin's tutorial yesterday, you'll know these as irreps. And that is to say that under transformation by the unitary, observables, as they move around in these small subspaces, well, potentially small subspaces, they will stay within those subspaces. And so we can kind of track within these individual subspaces. And so given, if we have a polynomial-sized Lie algebra that's generating the unitary rotations, and we look at a particular subspace that is of polynomial dimension, and that could be, but it doesn't necessarily have to be the Lie algebra itself, then we can compute dynamics within the subspace. If we take a basis of the Lie algebra and the invariant subspace, then we can compute our dynamics entirely in terms of these structure constants F. And so basically that means that the dynamics of the observables that we care about are going to be entirely determined by dim G number of matrices of size dim L times dim L, where this is our invariant subspace. So let's just kind of justify these numbers. We know that the subspace L is invariant. It's closed under these operations. So when we're tracking where can the operator go, it can only go to dim L possible places, which gives us the dimension of these matrices. And then our rotations are generated by the Lie algebra, dim G, so there's only dim G possible directions that we can be driven in. So another helpful feature of this formalism is that we can also include noise channels. As long as the Krauss operators of our noise channel leave the subspace invariant, then we can simulate this. And there are far more operations that will do this than like just those in the Lie group. So as a really nice example of this, if the algebra has a Pauli basis, then the Krauss operators that we can simulate are any Clifford operations, since the Cliffords are going to normalize the Pauli group. And this is really helpful because it includes arbitrary Pauli channels, and many different noise models can be twirled into a Pauli noise channel. And note that any Pauli operators can be used as our Krauss operators in that case, not just those in the algebra. So taking a step back for a moment, these Lie-algebraic classical simulation techniques have been around for quite some time. So what have we done that's actually new? So we've taken these tools and we've reformulated them in a gate-based framework that's amenable to quantum computing. And we've asymptotically improved the complexity of evolution for these gate-based approaches. In the cases where a Pauli basis algebra is used, we also provide guidelines for even more efficient implementation via sparse methods. And as I've just described, we've mathematically generalized this framework to include general invariant subspaces, not just the Lie algebra itself, and so that generalizes us to include more observables and expand the scope of classical simulability. Everything in our approach is easily differentiable, which is really helpful when you're like us and working in a QML setting. And in contrast to previous approaches, our simulation method supports arbitrary initial states as long as you know the observables of the basis elements in your subspace. So this means, as Marco said, if you can prepare an input state on a quantum computer efficiently, and then you undergo some sort of polynomial data gathering phase, then you can run GSIM on that initial state regardless of whether it has any special structure. So notably, these generalizations enable some simulations that, to the best of my knowledge, can't be done with any other method. So here I'm simulating the dynamics of this disordered Ising Hamiltonian for 200 qubits. And this Hamiltonian is simulable with fermionic linear optics, but what I'm doing is I'm simulating it with an initial state, which is a magic state for fermionic linear optics, and in fact it has exponential fermionic extent, so it's going to be exponentially expensive in those methods. It's quite easy to get the classical representation of this state analytically, and we can then go ahead and simulate it both without noise, as I've depicted here, and with some random Pauli noise, as I've simulated here. But notably, these simulations are exact. There's no approximations involved in this. And so as a result of that, when we add noise and we kind of dissipate these oscillations, we can still see the remaining oscillations that are like a factor of 10 to the 6 smaller. This stands in contrast to a lot of other methods for efficient simulation of noisy circuits, because sometimes they rely upon like truncation of low weight dynamics that are drowned out by noise. So this is a sort of interesting case of simulating noisy dynamics exactly and still being able to resolve these very small fluctuations. This implementation is quite efficient, so this is for 200 qubits, and it ran in something like 16 minutes on a single CPU core. This, of course, is going to be heavily dependent on the algebra that you use. So now, with the remaining time, I will try and rapidly summarize some of the applications that we demonstrated. So first, I note that the dimension of the Lie algebra is also connected to overparameterization. For my purposes, basically this means that anytime I can classically simulate it, I can also efficiently optimize it and guarantee that I'll get to a good solution. And so the plot was just kind of a simulation of that in GSIM. Now, as Marco said, and perhaps rather pessimistically, for pre-training, which is a bit awkward for me now, but barren plateaus are a feature of the landscape on average. And so if we can initialize with smart parameters, then maybe we can avoid this. So GSIM can help with this. So take, for example, the example of this transverse field Ising model. That's efficiently simulable in GSIM, but if we add just one term, this longitudinal field, then suddenly it's got a barren plateau, it's not classically simulable, and it's potentially non-trivial. And so it's sometimes the case like this that a problem with an exponential Lie algebra is connected to something with like a polynomial Lie algebra in some manner, maybe the addition of one term. And so the strategy then will be to use GSIM on a classical computer to solve this easier model first, and then transfer those parameters over to the full quantum model and finish your optimization on a quantum computer. And so here, this is just kind of a single training trajectory where we see that pre-training did actually help us. And looking at this more systematically, we tested this out for VQE, and we found that for this particular problem, it really did help on average, consistently getting better training. And in fact, we also found that this mitigated barren plateau problem. So when we initialized randomly, we got this kind of nasty exponentially vanishing gradient variance. But then when we pre-trained it with GSIM, we found that the gradients were a lot nicer. The barren plateau effect was at least mitigated. Similarly, we can also go and apply this to QAOA. So what we did was we applied this to QAOA on a path graph. You could also do a complete graph or a cycle graph, and this is classically efficient in GSIM. And then transferred this parameters to more complicated graphs. And so we found that for the two tested types of random graphs we considered, this improved the solution convergence on a majority of the solutions. One more application that we considered was variational compilation of quantum circuits. So in variational circuit compilation, we consider some target unitary V that we want to approximately implement on a quantum computer. And then we have some parameterized ansatz, and we try and optimize that to implement this target. So typically this would require a Hilbert-Schmidt test, which in general would require quantum resources. But using GSIM, we can compute a proxy to the Hilbert-Schmidt test and then use that to optimize the circuit. And so we tried this, and we found that it performs quite well in a sort of random benchmarking test. And so then as a more concrete example of this variational compilation, we looked at synthesizing time evolution unitaries. And so here I'm considering the compilation of unitaries for this disordered spin model, which should show the onset of Anderson localization. And doing a trotterization, we found that, of course, the dynamics are quite bad fidelity after even a short time. Then taking that same ansatz structure for a trotter circuit and optimizing the parameters in GSIM, we got far better fidelity evolution. And the last application that I'll talk about today is supervised quantum machine learning tasks. So things like, in this case, classifying ground states of a Hamiltonian across some phase transition. If we're using a variational QNN for this that has a polynomial-sized algebra, then we can run it on a classical computer with GSIM, so long as we are classifying using the compatible observables, and we are given or we acquire the observables for the input states. So the input, as with any classical simulation, will be these observable measurements. And so in our paper, we demonstrated this by training a classifier for a 50-qubit disguised Ising model. But this is kind of like, sort of baby's first QML model, and in and of itself, it's not that interesting. What is quite interesting is the implications for how you do inference with a trained quantum classifier. So for these models, they're classically simulable, and so obviously there's not going to be any quantum advantage for learning from data. But what about inference on unseen data after we've trained? So let's say you've trained some classically simulable model in GSIM, and now you're given a new state that you want to classify using this trained model. And so the kind of obvious way to approach this is like, we've trained it with GSIM, we know it's classically simulable in GSIM, so why don't we just classify it in GSIM? And so we can do this. So to do this, we first have to make a polynomial number of measurements on this state. It doesn't matter what we want to measure, we always need the classical representation to run something in GSIM, so this will always be poly n measurements. Then we take these measurements, we plug them into GSIM, we run it on a classical computer, and that will give us the output, an inferred label, which will tell us what the classifier thinks this new state is. But that is not the only way that we can do this. So an alternative is we've got a quantum state, we've got a quantum circuit, and we know the parameters, so why don't we just run that on a quantum computer? So we take the state, generate it on our quantum computer, run it on a QPU, and then now we can just measure the observable, but we only need to measure one observable because we know what our order parameter for this is. So we do far fewer measurements than we needed to in the GSIM case, and that will give us our output. And so while there's no advantage to training the model on a quantum computer, that is, there's no quantum advantage for learning, it might be the case that in terms of measurement resources, this approach is going to be cheaper. And so this gives us this notion of like training things, so classical training followed by quantum deployment, which leaves a little bit of scope for utility of these models. And we think that this could be particularly interesting for things like quantum metrology, where you don't really care whether or not something is classically simulable. You don't care about computational advantage. You just want to extract information as cheaply as possible in terms of measurement resources. So that leaves open a future avenue. So thank you again to my wonderful collaborators and to the Quantum Computing Summer School at LANL for getting this project started. It has been truly amazing working with them over my PhD, and honestly, it really made my PhD, so I encourage anyone who wants to do it to go for it. We'll have an updated manuscript coming out very soon with these generalized invariant subspace formalisms in it. And also, as Marco said, I am wrapping up my PhD very soon. I actually probably will submit my thesis from the hotel room this week. So if anyone is looking for postdocs, industry jobs, please come talk to me. I'd love to have a chat. So thank you.
Great, so it sounds like there's a deal, $4. That's really, okay. Great, do we have some questions in the room? Maybe 2 quick ones. Okay, so maybe I can get started, right? We heard about many applications of GSIM. Where would you put this in comparison to tensor networks, for example, right? Or other classical simulation methods? We know a couple ones right now, and they all have different advantages. So really, when would you suggest me to use GSIM in comparison to, a light cone or a tensor network simulation method?
Yeah. So I guess the sort of straightforward answer to that is if you have a polynomial Lie algebra, there's just no point in doing it if you don't, because it will be exponentially expensive. And so that will be for very specific structured problems where you have some sort of free fermionic structure in the case that we considered, or Eric has a nice paper on doing this for permutation invariant systems. So it really is going to be constrained to certain kind of circuit evolution structures rather than limited by, say, entanglement in the tensor network case. I guess the sort of, cop out, holding hands, everyone's very happy answer is there is a real zoo of classical simulation methods, and I think one always needs to have all of them in mind and just decide what's most suitable for a particular problem. Okay,
thanks a lot.
Maybe a quick question. The Pauli Lie algebras can be classified, and they are kind of either exponentially large, or they are kind of a fermionic type, or Majorana fermionic type. Where would such a classification help in your picture? I mean, is it clear that it's kind of that all interesting algebras are kind of too large to be tackled properly?
Sorry, I didn't hear that last bit.
I mean, is it true that then all interesting Lie algebras are kind of too large to be interesting in your framework?
I don't think so, and I think also a distinction needs to be made between the structure of the sort of algebraic structure of your data itself and your initial states, and the algebraic structure of your classifier. And so I think it's rather an open problem whether you can take more structured data that is generated by complicated states on a quantum computer, measure those observables, and then do something interesting with these sort of limited structure circuits. It seems that you can't do everything with that, but it seems that there's something you can do with that.
Great, then we had a question on this side.
Hi Matt, thanks for your presentation. Just wanted to ask, as a user, should I just specify the structure constants of the whatever Lie algebra I want to explore? For instance, I think you here focused quite a lot on poly algebras, but maybe for applications in quantum optics, as you said in metrology, for example, there are different sorts of algebras. So as a user, should we just specify those structure constants and that's it?
So as an input for the algorithm, you need to have computed the structure constants somehow. Those are an inherent property of the algebra, which will just come from, give a set of generators and there is a defined set of structure constants. I guess in the case of quantum metrology or quantum optics, where people are often dealing with bosonic algebras, the Hilbert spaces are infinite dimension. I guess there's some interesting other papers that talk about taking infinite dimensional Hilbert space bosonic systems and mapping them to finite Lie algebras.
There will be the same, even if they are infinite dimensional, the number of generators can be finite and can be very small for many applications. So I'm just wondering, if you have the same sort of finite number of structure constants, so one should be able to use GSIM for this, right?
Yes, and there's a nice paper by a guy called Ruvi Lekamwezem. I think I'm pronouncing his name all right. I'm actually friends with him, so it's embarrassing if I'm not, but who does this for bosonic systems as well.
Okay, let's thank Matt again.